with these dementia-related issues. So this is a major concern, this sleeping disorders. What are the solutions? Okay, there are basically 3 areas where people have done research in terms of solutions. One is music therapy. Harp music, for example, has been quite effective for helping people sleep. Unfortunately, for people with dementia, it has no effect. So if people have dementia, the music is not. My mother, for example, when she was reasonably high functioning, harp music would help her to relax and go to sleep. But as her dementia progressed, she hated harp music. Her love for the music stopped. So it was no longer something that was helpful for helping her go to sleep. The second key issue, possibility, has been drugs. In particular, melatonin and a number of psychiatric drugs. There are a number of key problems with these drugs. One, they have law of diminishing effect. In other words, I can give a person melatonin, it may have some effect today. Within about 2 or 3 weeks, I need to double the dose. Then I need to increase the dosage. Then I need to increase the dosage. And I need to increase the dosage. As the dosage increases, the person is knocked out at night, but the major side effect is unstable walking during the daytime. This unstable walking leads to falls, and 20% when a person falls, 20% of these falls may result in hospitalization, and 20% hospitalization results in death. Okay, so the fall becomes the cause of the death. So clearly we don't want to use drugs. They're basically a failure solution, but they are used because, as the person in long-term care facilities generally state, there aren't any other valid, we don't have any other tools. Okay, that brings us to our final effort, is to try to use light to try to help these sufferers of dementia, or people living with dementia, I believe is the correct term. Okay, and that is what I'd like to talk about primarily today. Okay. All right, now, let's look. Why? How does our eyes processing of light? Okay, this is, I think, an important thing that we need to first consider. How is light being processed, and how is it setting our clocks? Okay, by 1944, you may argue about the date, I believe vision is pretty well understood. I would say in the last 80 years, we've made a little bit of more knowledge, but not that much. We know about cones, rods, and how they affect vision, right? How our back of our eyes, we are sensitive to blue light, green light, or red light through the cones. We get, when there's a low level of lighting, the rods take over, and we can see black and white and grayscale for low level of intensity at low lux levels. This is quite understood. But there has always been one haunting question for the last 50 or 60 years. Why can blind people know when it's day and night? Why do blind people know that it's day or night? They can't see anything, yet they know it is day, and they know when it's night. Okay? That brings us to the discovery of the 4-sensor PRGC. Our eyes have 4 billion RGC cells. 4 billion. Of these 4 billion cells, 3,000 3,000, that's 1 in, whatever, 3,000 out of 1 billion are light sensitive. Okay, these light sensitive cells are located not at the back of the eye, but at the very front of the eye. Okay, so if your back system is all broken, they are still sensitive to light. They don't go through the vision system. They send information directly to your circadian part of your brain, which controls the hormone melatonin. The more light hitting these sensors, the lower level of melatonin you have in you. Melatonin causes you to want to go to sleep. If you depress the level of melatonin, you want to stay awake. Okay? And when these do not receive any cells, melatonin goes up in your cell. Now, this sensor was first discovered in 1998 in fish. In 2002 was when this Nature paper was published talking about this in human beings having these cells. And in 2016 is when we see more information publishing about how this is sending a direct signal to the clock and how the melatonin suppression works. Okay, so this is basically the background. Now, let's move back to my dear mother. Why is my mother's clock mixed up? Okay? In this one, I want to show, we got a lot of stuff on this graph, so I'll try to slowly go through it. Okay. My bottom scale is wavelength in nanometers. This scale is using sensitivity. This scale is irradiance. Okay. Look, first of all, the gray line gives me my solar, a rough solar irradiance spectrum. So that's basically the relative intensity of light from the solar spectrum. Okay. Here, this would be the sensitivity of the blue for blue light. Our sensitivity for our green, the cone responsible for green. And our sensitivity for the cone responsible for red. Okay. Now, we will note that there is a hole in here, and the cells that control RPG, the photoreceptive cells, RGC cells, they absorb right here around 490. Okay? There's some concern, there's some differences in the literature about where the spectrum actually is, so I try to just take a rough one, but basically here. Now, this is the wavelength of light in the sun that is telling you whether it's day or night. Now, let's look at traditional design of lighting. Like the fluorescent lights are designed, have this sort of a wavelength. We have a little bit of stuff down here which we don't really want. We have a nice spike here to excite our blue cones. We continue along. We have a nice spike here to efficiently hit our green cones. And another little spike here to help us with the red. You notice something from this graph? There isn't any light coming out at this wavelength where these cells that are responsible for telling us day or night absorb. So now I come back to my mother's case. My mother, when she goes back to the long-term care facility, it's fluorescent lighting. She's inside. The fluorescent lights are turned on in the morning when she gets up, but they're providing no stimulation at this wavelength, so she's not going to be very much awake, so she feels free to nap. It's the same intensity of fluorescent light all day until they say, oh, it's 9 o'clock. It's time for you to go to bed. Let's turn off the light. So she is not getting any of this dynamic solar lighting. If she was outside throughout the day, the amount of wavelength that this will be changing. It would be telling her, oh, it's morning time, it's time to work hard. We've got lots of stimulation. Oh, it's 6 o'clock. The total lux here has dropped. It's getting ready time for me to be relaxing. My melatonin is going up. And continues. So now we can say, okay, this is a problem of CFL, but I think if